So we want to get started on rotational energy, angular momentum. All of these things go together and pile into one expanded kind of thing from what we were doing with regular linear momentum and energy in terms of straight line motions that things take. And now, in addition to that, instead of pretending that objects that are in motion can be treated like a point particle, now we're going to talk about extended bodies, or meaning multi-point particle model. So we're going to account for all of the particles in an object when it's in some sort of rotational state. And so what we would be good to do first is kind of go from our point particle energy kind of thinking. So if kinetic energy is 1/2 mv squared for a point particle, and if you recall, and I hope you do, is that when we use the letter V, we're referring to a linear speed. So if we're going to move that to a rotating frame, then we're going to have 1/2 mass times, instead of V, we're going to have omega r. And I hope you remember from our rotation section that the linear speed of an object in circular motion is going to be equal to its angular speed times the radius, a constant radius associated with that circular motion. That would be the English way to understand V equals omega, that funny looking WR, is when you have something that's in circular motion, it has a linear speed, V, that's tangent to the path, and an angular speed, that's how fast it's sweeping out some angle. So a little picture time, I guess. So here's some circular path, and there would be some object whose linear speed would be V, but whose angular speed would be omega. So a bicycle wheel is a perfect example of something that has both translational kinetic energy, and that's what we mean over here. This is translational kinetic energy because it's dealing with an object moving as a point along a straight line. That's what V represents. But if the point that we're paying attention to, say something stuck on the wheel, okay, say it's the cap on the valve stem of this bicycle wheel, well, that thing is moving through space and it's kind of bobbing up and down like a half circle, but it's also going round and round and round all the time around a circle. So there's some sort of angular speed that it has, meaning how fast does it sweep out 2 pi. Okay, and so that's a little translation from one to the other. If I take it from a linear point particle, and I'm still doing linear point particle at this point in the thing, but what we're trying to do is how do I go from this to accounting for all of the point particles in a system. And so what we can do is kind of rearrange this a little bit. The 1/2 is a constant, the mass is a constant. And omega r, if I square omega r, I'm going to get omega squared r squared. So I could write r squared omega squared, and what that does is it allows me to kind of keep these features of the system separate from the numeric constant and the speed part of this energy statement. Our old school stuff of a point particle moving, the v squared referred to the linear speed, whatever squaring speed means. All right? And now I've changed that v to be in terms of its angular speed, which required the constant of the radius in there. And now it's omega squared. So now I have this different thing. When I account for the angular speed, an angular speed is the same throughout the entire object. Every point particle along the radius has the same angular speed. Their linear speeds are all different, as each little chunk outward or inward along the radius has a greater or smaller speed. The closer you are to the center, the slower your speed. The faster the farther you are away from the center, the faster the speed is, because it has to keep up with everything from between it and the center. All right? And so now we've sort of halfway, no pun intended, but it works pretty well given that we have a half in the equation. Get it? So we're halfway to kind of going from point particle to multi-point particle, but not the full business here. So if I were going to do rotational kinetic energy, that's a pretty bad spelling of rotational. Rotational kinetic energy, I would have to sum up all of the translational kinetic energy components. So that little sub I on the K is an index, a counter for all the point particles. So let me be clear here. So add up all of the point particle kinetic energies. That's what that I is referring to. Well, if I'm going to do that, then I need to kind of pull things together from what we just wrote at the top of the page into that first line. I have this 1/2, and I have something else and my omega squared. So this still is very kinetic energy-ish because it's got a half something speed squared. Kinetic energy has that feature going for it, but now I have, if I'm going to be counting every individual, or the ith, I equals 1, I equals 2, if I could put a label on every little point particle, 1, 2, to whatever, then I would have the mass of the particle I and the radius of particle I squared. So that, now I am counting up all of the individual rotational kinetic energies of this system, which is some extended body, a disk, a hoop, a wheel, whatever's going roundy-roundy. If it's going roundy-roundy, it's got rotational energy. If the roundy-roundy thing is also moving along a straight line, then it's got translational kinetic energy as well. All right, it's got two kinds of energies going for it. Now, this thing we call this thing here the rotational inertia. You might recall, and I hope you recall, that the M that this is just regular old inertia here. Mass is a measure of inertia. And when we speak of inertia, mass is the most natural and common way to frame what is meant by inertia, the property of an object to resist a change in motion. The more massive it is, the easier it is for that object to not be moved. The less massive it is, the more likely it is to be moved by the same force. Right? So if every point particle has a mass and therefore it has this inertia associated with it, then a collection of point particles in an extended body collectively have an inertia. And in this case, since these point particles are all going roundy, they have angular speed that's not zero, then this is a rotational inertia. All right, so you've been on or near spinning things. It's a different sort of thing, slowing them down, changing their motion. It's different. And so that's because of the nature of the beast, so to speak, to be this. And so one might call this, you could say it's the rotational mass. That's sort of sloppy. But rotational inertia, that's what we call it. And we like to give it the letter I. Capital I. So we're going to start, when things are going roundy, our factors of M for mass are buried within the rotational inertia, which we call capital I. So a ball has an mr squared to it. A disc, has the same thing. A hoop might have a 1/2 mr squared, or a wheel might have a 1/8 mr squared. There's all sorts of, and we'll see a table of different shapes that will show up in problems, and you'll use those standard formulas for rotational inertia of this versus the rotational inertia of that. But they all have this basic structure of mr squared, right? And that the m has to be there because every particle has mass. The r squared comes in simply from translating from a linear speed to an angular speed. You get that radius squared. And that radius is referring to where that point particle is located in the extended body. When I add them all up, I get these nifty little formulas. So that's the long and short of what we mean by rotational inertia. And I guess our final thing to write would be that K rotational, or K rod, or K sub r, would be 1/2 I omega squared. So here's our rotational kinetic energy equation. Looks a lot like our linear kinetic energy equation at the top of the page. So there's a structural connection there. They both have this 1/2 times the way we're measuring inertia times the speed squared, and whatever speed is appropriate for that kind of motion, linear versus circular motion. So there's this symmetry, if you will, in the structure of kinetic energy. It's always 1/2 of the way we measure inertia times the nature of that speed squared. Okay, so two versions of kinetic energy, one for roundy-roundy and one for straighty-straighty, otherwise known as linear and rotational.